Hi everyone, I'm Neve and I'm a research scientist at PyOps. Our paper is called Chucky, a Succinct Cuckoo filter for LSM tree, and this is joint work with Moshe Twito, the CTO at PyOps. Since their inception, database systems have stored data across two layers of the memory hierarchy: storage devices, typically spinning disks, and memory devices, typically DRAM chips. Memory devices are fast but expensive, while storage devices are slow but cheap. Due to these properties, it made sense for database systems to store most of the data in storage and to store a smaller amount of metadata to index data in storage so that it can be retrieved quickly. Over the past 15 years, however, solid-state drives have replaced spinning disks across a wide number of applications. These SSDs are significantly faster than spinning disks. Overall, this shrinking performance gap between main memory and storage is causing the metadata stored by database systems in memory to now emerge as a noticeable performance overhead. Now in this presentation, I want to talk about this problem in the context of LSM tree, or the log structured merge tree. This data structure is used today across a wide number of key value stores and storage engines in industry. And it uses probabilistic structures called Bloom filters in memory to facilitate queries. So as I'll show, these Bloom filters are now emerging as a performance bottleneck due to the shrinking performance gap between memory and SSDs. And so we'll explore some ways of how we can address this problem. So let's start with some background on how LSM tree works. LSM tree consists of a buffer in main memory that ingests entries inserted by the application. Whenever this buffer fills up, we sort its contents by key and flush it to storage as a sorted array called a run. LSM tree sort merges the runs in the background to restrict the overall number of runs that exist in the system, and it organizes them across levels of exponentially increasing capacities. An LSM tree can implement a lazy merge policy, meaning each level just gathers runs, and only when it reaches capacity, it merges them into a single run that gets placed at the next largest level. Such a design is better suited for writes, and it's often referred to as tiering. On the other hand, an LSM tree can implement a greedy merge policy, in which case each level contains just one run. Whenever this run reaches the level's capacity, it gets merged into the run at the next largest level. And this design is better suited for reads and often referred to as leveling. With either of these designs, the number of levels L in the LSM tree is log of n. In order to facilitate queries, there are typically fence pointers in main memory, which comprise the first key of every storage block of every run in main memory. These fence pointers allow us to find the relevant key range at each run with a single storage I/O. In addition to the fence pointers, there are Bloom filters in main memory, one for each run. A Bloom filter is a probabilistic data structure used to answer set membership queries. A Bloom filter can return a true negative, which is great for performance because it allows skipping issuing a storage I/O to a run that doesn't contain relevant data. It can return a false positive, which is bad for performance because it forces us to access a run that doesn't contain what we're looking for. Or it can return a true positive, in which case we actually find the key we're looking for and the read terminates. A concerning property of Bloom filters is that they're immutable, meaning they cannot be resized or updated once created. This means that during a merge operation, we need to get rid or dispose of the original Bloom filters of the original runs included in the merge and create a new Bloom filter during the merge for the new run being created. This in turn means that the Bloom filter's write amplification is equal to the LSM tree's write amplification. Or in other words, for every time that an entry participates in a merge operation in the LSM tree, that entry also has to be inserted into a new Bloom filter. Now, for all designs that we're aware of in industry, the Bloom filters are assigned the same false positive rate. By summing up this false positive rate across all the Bloom filters, we obtain an expression of f, the false positive rate, times log of n. This expression can be interpreted as the number of storage I/O on expectation that don't do any useful work during a query. In 2017, however, at Sigmod, we had a paper called Monkey, which showed how to optimally assign false positive rates to Bloom filters across different levels so as to minimize the overall false positive rate for the LSM tree. The result was that it's better to set exponentially decreasing false positive rates for smaller levels. This causes the sum of false positive rates to converge into a term that's independent of the number of levels and thereby shave a log of n factor from query complexity. This final expression for the overall LSM tree's false positive rate can be expressed as e to the power of minus m, where m is the number of bits per entry, times natural log of n. So this expression represents the state-of-the-art false positive rates that LSM trees can achieve. So the problem we address in this paper is the shrinking memory versus storage performance gap. Today, a memory access costs approximately 100 nanoseconds, while an Intel Optane SSD has an access latency of approximately 10 microseconds. This is only a 2 order of magnitude performance difference. The first manifestation of this problem is that with greedy LSM trees merge policies, which have a high write amplification, Bloom filter insertions can emerge as a performance bottleneck. The reason is that Bloom filter insertions have a random access pattern, which can lead to at least one memory access for each Bloom filter insertion. On the other hand, merge operations on the SSD have a sequential access pattern, meaning that write amplification gets amortized by the block size B, which stands for the number of entries fitting into a storage block. The second manifestation of this problem is read amplification during lazy merge policies. In this case, having to access potentially every Bloom filter at a cost of at least one memory access per probe can approach and even exceed the latency of the SSD I/O ultimately issued to retrieve the target entry from storage. So overall, we see that across the entire spectrum of LSM tree designs, the Bloom filters are emerging as a performance bottleneck. With greedy policies, the problem is Bloom filter insertions, while with lazy merge policies, the problem is Bloom filter probing. To make things worse, as the data size grows and there are more levels across which Bloom filters get reconstructed and queried, the trade-off curve gets moved outwards, away from the origin of the curve, of the graph, leaving applications with fundamentally worse trade-offs to choose between. So our goal in this work is to devise a new data structure as a replacement for the Bloom filters, which achieves fundamentally better trade-offs than the current trade-off curve which Bloom filters enable. However, there are two constraints which any solution to this problem would have to abide to. The first one is it would have to achieve a modest memory footprint in the area of 10 bits per entry, which is what Bloom filters require today. The second constraint is that any replacement would have to achieve a low false positive rate, in line with what state-of-the-art Bloom filters achieve today, as shown by this expression here that we saw before. So to address all these problems, we introduced Chucky, which stands for Huffman-coded key value store. Chucky replaces the Bloom filters of an LSM tree by a single hash table that maps from every key in the system to the level ID whereon the corresponding entry resides in storage. So for example, if we have an entry X, at level 2 of the LSM tree, we'll have a mapping entry mapping from X to 2 inside the hash table. Whenever a merge operation takes place and an entry gets moved to a new level, we take the opportunity to also update the level ID for that entry in the hash table. In the case of a lazy merge policy, where there are several runs per level, we can map the individual run whereon the entry resides rather than the level ID. So overall, this design offers probes in constant time due to the hash table design. And furthermore, each entry's level ID only gets changed once every time an entry moves into a new level. And this gives us a log of n access cost for updates. So overall, this new design stands to offer far better trade-offs in terms of memory accesses for reads and writes than Bloom filters do. While our design so far stands to achieve good in-memory performance, it still doesn't meet all the success criteria we've set out to achieve. In particular, storing the keys of all entries within this hash table in memory can by far exceed the amount of main memory taken up by Bloom filters. So rather than storing the full keys in memory, we're instead going to store a fingerprint for each key, where a fingerprint is a hash digest obtained by hashing each key. For example, instead of storing the full key X, we can store a 5-bit fingerprint for this key, mapping it to level ID 2. The problem with storing fingerprints, though, is that they can lead to false positives. In this example, we're querying for a key Y, which exists at level 3 of the LSM tree. Now, suppose this key happens to map to the same hash bucket and have the same fingerprint as key X. In In this case, we're going to have a false positive match for level 2, which is going to lead to one redundant storage access. So now this begs the question of what is a false positive rate with our design of Chucky so far. We can analyze this using minimal perfect hashing for simplicity, though in the paper we actually give a more precise analysis. So the false positive rate is 2 to the power of minus f, where f is the fingerprint size. Now suppose that we have an overall main memory budget of m bits per entry. Of these m bits, some of them have to be dedicated to store level IDs. Now suppose that we store the level IDs using an integer encoding. This implies that the size of each level ID occupies log base 2 of L bits, where L is the number of levels. This in turn implies that the number of fingerprint bits is the overall main memory budget minus the encoding size for the level IDs. We can now plug this fingerprint expression into our false positive expression to obtain a false positive expression that's comparable with that of Bloom filters. And what we observe is that at this point, our false positive rate for Chucky is still higher than that of Bloom filters. And the culprit is this log of n factor, which causes the false positive rate with Chucky to deteriorate with respect to data size, unlike the false positive rate of Bloom filters. The culprit here is the integer encoding for the level IDs. So specifically, as the data size grows and there are more levels in the tree, the level IDs need to grow too to be able to represent more levels uniquely. Therefore, the level ID is still bits that would have otherwise been used for the fingerprints. And this causes the fingerprints to shrink as the data size grows, and thus the false positive rate to increase as the data size grows. To address this problem, we observe that most level IDs within the hash table correspond to the largest level of the LSM tree, while exponentially fewer level IDs within the hash table correspond to smaller levels. This is simply due to the data distribution of entries across the different levels of the LSM tree. And our insight is that this skewed distribution makes the level IDs extremely compressible, specifically by encoding level IDs of larger levels with fewer bits. For example, suppose we use a unary encoding to represent the level IDs. In this case, 1 represents level ID 5, 01 represents level ID 4, etc. Note that if we had a lazy LSM tree with multiple runs per level, we could extend this encoding by assigning an integer to represent each one of the runs within a level, and then appending that as a suffix to each unary encoding to allow us to represent each one of the runs uniquely. Now, the core smarts behind this method is that even though smaller levels now have a larger encoding than they had before, they're also exponentially less frequent within the LSM tree. And this in turn means that the average encoding length converges to a constant that's independent of the number of levels. Specifically, we showed that for a level LSM tree, the average code length is never more than 2 bits per entry. This is better than the log of n bits per entry that we had before with an integer encoding for the level IDs. This in turn guarantees that the average fingerprint length is also going to stay constant as the data size grows, which promises to keep the false positive rate stable as the data size grows. So now we have the promise of a data structure that offers better in-memory performance than Bloom filters, while offering approximately the same false positive rate for a similar main memory budget. An interesting problem that emerges with Chucky is that the variable length level ID codes can lead to alignment issues within buckets. To see this, consider a 16-bit bucket with 2 entries. First, suppose that both entries within that bucket come from the largest level of the LSM tree. In this case, they'll tend to have shorter level ID codes, which could lead to an underflow, meaning here there are 2 bits at the end of the bucket which are not getting used. This leads to poor memory utilization. On the other hand, suppose both entries in the bucket come from the largest level. In this case, they'll tend to have longer level ID codes, which could lead to an overflow, meaning in this case, there's 17 bits that need to be stored, but the bucket only contains 16 bits. To mitigate underflows and overflows so as to maximize memory efficiency and utilization, the first step we take is to assign larger fingerprints to larger levels of the LSM tree to make up for the fact that they tend to have shorter codes. So for example, we can set longer fingerprints here to entries from the largest level to seize up and exploit the underflowing bits. And we can assign a shorter fingerprint to one of the smaller levels to remove the overflow. A second step we take is to co-encode multiple level IDs within a bucket as a single code at the beginning of the bucket. In the paper, we showed that by co-encoding multiple level IDs as one, we can achieve a more concise encoding, and in fact use any saved bits to further increase the fingerprint size in some of the levels. To make this concrete, here I'm enumerating all the different level ID combinations that can coincide for two entries within a bucket for an LSM tree with 3 levels. We see that there is a unique code that identifies the given combination at the start of the bucket, followed by the fingerprints corresponding to the entries in the bucket. In order to assign a fingerprint length for each level, as well as to choose a code for each combination of levels that may coincide within a level, we introduce the following efficient workflow. The first step is to frame and solve a constraint optimization problem, whereby the goal is to maximize the average fingerprint size, subject to the constraint that the remaining space after the fingerprints should be able to support a uniquely decodable code for all level ID combinations. The second step is to actually generate codes for all level ID combinations. Now, in the paper, we show how to solve this problem concretely. Here, we'll just give some hints. We solved the constraint optimization problem using hill climbing, and we use a Kraft-McMillan inequality to ensure that there's enough space for the level ID combination codes. And finally, we use Huffman coding to actually generate a prefix code for all level ID combinations. Another important issue in the hash table design is that the number of entries that map to each individual bucket may be highly variable, thereby also leading to overflows and underflows. This can also jeopardize memory efficiency and utilization. To address this problem, we structure the hash table as a Cuckoo filter, whereby each entry is mapped to 2 buckets and can be swapped across them using the fingerprint of the entry. Now, if both buckets that an entry maps to are full, some entries randomly selected from one of the buckets and swapped to its own alternative location. Such a design is known to achieve a 95% space utilization. In the first experiment, we measured the false positive rate over a lazy LSM tree as we increased the data size measured in terms of number of levels. We observed that with the uniform Bloom filters with fixed false positive rates, the overall false positive rate across the LSM tree increases with data size, while with Monkey, which assigns variable and optimal false positive rates to different Bloom filters at different levels, the false positive rate stays fixed with data growth. Chucky is able to match the false positive rate of Monkey by virtue of compressing its level ID information and thus allowing fingerprints to stay large as the data size grows. In the second experiment, we measure query latency as we increase the data size. We observe that the performance of Bloom filters gradually deteriorates with data size as there are more Bloom filters across more levels that need to be accessed. Chucky, however, replaces the Bloom filters by a single hash table, which maintains a constant time access cost, even as data grows. In the final experiment, we increased merge greediness for a leveled LSM tree by increasing the capacity ratio between adjacent levels of the LSM tree. We observed that Bloom filters have far more rapidly deteriorating performance. The reason is that they're mutable, and so as we increase merge greediness, the rate at which we reconstruct Bloom filters also increases. On the other hand, Chucky is mutable and supports more modest maintenance overheads than with Bloom filters, and so performance stays far more robust as we increase merge greediness. So overall, we introduced Chucky to replace the Bloom filters for an LSM tree with a hash table that maps from the fingerprint of every entry in the dataset to its location within the LSM tree, and that compresses this location information to keep the false positive rate and the memory requirement modest. By so doing, Chucky achieves better read-write memory efficiency and also allows maintaining the same false positive rate as state-of-the-art Bloom filters. So that's all for now, and thanks very much.